China spent $1 billion on glass. Not chips, not rare earths, not oil, glass. And right now, some of the most powerful tech companies on Earth are scrambling to catch up in a race they didn't even know had started. Here's something that sounds completely made up. The single most important material in the next decade of computing power isn't silicon. It isn't some exotic metal pulled out of a mountain in the Congo. It's glass, engineered glass, thinner than a human hair, flatter than anything nature can produce on its own. And while the entire world was staring at one thing, China quietly went and made the other thing the battleground that actually decides who wins. Stay with me, because this is not about your phone screen. This is not about Windows. The glass at the center of this story is nothing like anything you've ever held. And by the time the West realized what was happening, the biggest early moves had already been made. Now here's the part that should make you uncomfortable. This didn't sneak up on anybody because it was hidden. It wasn't classified. The factories, the patents, the investment funds, all of it was public. Every single piece. It just wasn't being watched. Because for years, everyone who cared about the chip war was locked onto the same obsession. Transistors. Who can make them smaller? Who can print more of them? Who can hit the next node before the other guy? That conversation ate the headlines. It shaped government policy. It dictated hundreds of billions of dollars in investment. And while that conversation roared at full volume, a quieter one was happening about the layer underneath the chip, the part that holds the whole thing together, the part that, it turns out, is now the most important battleground in the entire industry. And the part where China moved first. If you're into stories like this, the ones that get underneath the headlines and tell you what's actually happening before the rest of the world catches on, subscribe right now and turn on notifications. This channel covers the strategic moves that matter. Materials, supply chains, the decisions being made today that decide who runs the next decade. Hit subscribe so you don't miss what's coming. Now let's get into it. To understand why glass became a billion-dollar weapon, you first have to understand what it's replacing. So think about a city, a big modern city. Skyscrapers, subway lines, power grids, fiber running under every street. You can stand there and admire all of it. The architecture, the engineering, the sheer scale. But none of it works if the ground underneath shifts. The second the foundation moves, everything on top is compromised. It doesn't matter how elegant the design is or how many billions went into building it. A shaky foundation is a problem no amount of clever work above ground can ever fully fix. Computer chips have a foundation too. It's called a substrate. It's the base layer the chip sits on. It holds everything in place, routes the electrical signals between components, and helps carry away the heat. And for about 50 years, these substrates have been made from engineered plastics and resins. Layers of synthetic material bonded into something that looks, if you could hold it, like a very thin, very sophisticated piece of laminate. Not glamorous. Nobody makes a marketing video about substrate, but essential. In the exact same way the concrete footings under a skyscraper are essential. For most of chip history, this was fine. Early chips were small. The demands were modest. The plastic did its job and shut up. The problems started when the chips got dramatically more complex. And they got dramatically more complex because of one thing: artificial intelligence. Here's what changed. The chips powering today's most advanced AI aren't single chips anymore. They're clusters of smaller chips, chiplets, bundled together into one enormous, densely packed package. Memory chips, processing chips, communication chips, each one optimized for exactly what it does best, all working as one. It's genuinely brilliant engineering. But it created a problem that gets worse the bigger you go. Some of these chiplet packages now stretch beyond 8,000 square millimeters. Sit with that number. That's roughly the size of your phone screen. Now picture that entire surface packed with billions of microscopic connections, all trying to move data at once, at hundreds of gigabytes per second, while throwing off enough heat to shut down a laptop in seconds. At that scale, the substrate underneath stops being a passive holder. It becomes one of the most critical performance variables in the whole system. And here's where plastic falls apart. Literally. Plastic warps. When a plastic substrate heats up during operation, it expands. When the chip powers down, it cools and contracts. That cycle happens thousands of times over the life of a chip. Each individual movement is almost impossibly small. fractions of a millimeter, but at the scale of a modern AI package, where the connections are so fine they make a strand of DNA look like a rope, those tiny shifts pile up. Connections that lined up perfectly during manufacturing start to drift. Signals that should travel clean begin to distort. Performance degrades in ways that are inconsistent and miserable to diagnose. And in the worst cases, the connection just snaps and the chip dies. And here's the truly frustrating part. You can't see it coming. There's no crack, no obvious moment of failure. The damage is invisible right up until it isn't. Engineers fought this for years. Tighter tolerances, smarter designs, better quality control. It worked while the packages were small. But the next generation of AI chips is pushing into territory where those patches simply cannot hold. The material itself had to change. And the answer the industry landed on still makes people laugh when they first hear it. Glass. Now sit with how strange that sounds. We're talking about the foundation for the most powerful AI systems on Earth. Machines running at extreme speeds, under extreme heat, handling workloads worth billions. And the solution is the same basic stuff that gets swept off the kitchen floor after an accident. Except it isn't. Not even close. The glass going into next-gen chip substrates is a precisely engineered product built specifically for semiconductors. It shares the same basic chemistry as window glass, the way a Formula One car shares the same basic idea as a bicycle. Technically related, practically a different universe. Here's the cleanest way to feel the difference. Plastic under heat behaves like a rubber band. Stretch it, release it, heat it, cool it, and over time it loses its shape. It fatigues. It gets less predictable with every cycle. Glass under those exact same conditions behaves like a steel rod. Heat it, cool it, run it through thousands of thermal cycles, load it with stress, and it barely moves. And that stability buys you something enormous. Because the connections stay put, engineers can pack them far, far closer together. Here's the number that stops people cold. Glass substrates can support up to 10 times more interconnect density than today's best plastic. Not 10% more, 10 times more. Let that sink in. That's not an upgrade. That's a generational leap. 10 times more connections in the same physical space means chips that move data faster, lose less energy doing it, travel greater distances inside the package, and hold better signal fidelity than anything plastic could ever touch. And remember, the performance ceiling of an AI chip isn't just about the transistors inside it. It's about how fast data can move between the pieces. Improve the substrate dramatically, and you improve the entire system dramatically without touching a single transistor. Then it gets better. Glass moves heat better as packages grow, so you can run chips at their peak for longer. Glass leaks less signal, so at the insane data rates these chips run, you hold integrity that software could never recover. Every advantage stacks on the last one. So here's the obvious question. If glass is this good, why didn't the industry switch 10 years ago? Because making it is brutally, almost impossibly hard. The glass has to be flat to tolerances invisible to any instrument outside a specialized metrology lab. The holes drilled through it to carry the electrical pathways, called through-glass vias, are thinner than a human hair and have to be placed perfectly. And drilling holes through glass at that scale without introducing microscopic cracks that quietly spread and kill the chip weeks later, that's a manufacturing nightmare that has taken years of dedicated engineering just to approach. And that difficulty isn't a footnote. That difficulty is the entire story. Because whoever solves the manufacturing problem at scale controls the next layer of the global chip supply chain. And the race to solve it is already running, and it's further along than almost anyone realizes. Now here's where it gets insane. For most of the last decade, the entire chip war came down to a single machine, the extreme ultraviolet lithography machine built by a Dutch company called ASML. It is the only machine on Earth that can print transistors at the most advanced scales. No ASML machine, no leading-edge chip. So the United States and its allies spent years building an export control system designed to keep these machines out of certain countries. The logic was airtight. Block the machine, block the progress. Except that logic was built around one single path to better computing. And it is not the only path. Advanced packaging, the substrate layer, is a completely different road, and it does not need an ASML machine. It needs materials science, precision manufacturing, process engineering, capital, and patience, every one of which can be built independently with zero access to any export-controlled equipment. Now look at the move again. The decision to pour serious money into glass substrates wasn't just a technical bet. It was a strategic repositioning toward the exact part of the supply chain where America's whole containment strategy doesn't apply. And the money was real. China's national semiconductor investment funds have been directing capital specifically at advanced packaging since 2023. Multiple companies, multiple programs, all aimed at glass. The total crossing $1 billion across factories, equipment, patents, and talent. None of it classified, all of it publicly registered. It just didn't generate Western press because the West was busy watching lithography. And the company that makes this whole strategy click into focus is BOE. You may not know the name, but you've held their work. BOE is one of the largest display manufacturers on the planet. They make the precision glass panels inside hundreds of millions of phones, TVs, and monitors every year. And running that business requires large-scale precision glass infrastructure, specialized equipment, deep process knowledge, supply chains, and engineering talent built up over decades. Here's why their move into semiconductor-grade glass is so dangerous. That infrastructure overlaps massively with what glass substrate production demands. The equipment is related. The process knowledge transfers. The teams already have the expertise. This isn't BOE reinventing itself. It's BOE extending something it already built at massive scale and pointing it at the chip industry. Their program targets production-capable output running into 2026 and accelerating from there. So how did the rest of the world let this happen? They didn't, exactly. They just woke up late. And the response is more serious than most people watching from the outside understand. Because here's the twist. China moved first into glass as a strategy. But China is not the only one in the room, and some of these names are going to surprise you. Start with Intel. Intel has the longest track record in glass substrates of anyone on Earth. A program going back over a decade, which in semiconductor time is an eternity. In that span, they built one of the deepest patent portfolios in the field and worked through manufacturing problems most competitors haven't even hit yet. More recently, Intel shifted toward licensing. Instead of controlling production directly, it's sharing the technology and positioning itself as the intellectual property backbone of the entire glass ecosystem. A bet on being the foundation of the foundation. Smart for a company deep in its own restructuring. Then Samsung, which is further along than almost anyone outside realizes. They're running an active pilot line at their Sejong facility. Not a research project, an actual pilot line staffed by engineers hired specifically for glass substrate expertise. And in late 2025, Samsung Electromechanics signed a formal materials partnership with Sumitomo Chemical, one of Japan's largest specialty chemical companies, to lock in the specialized glass materials the process needs. Their internal roadmap targets commercial-scale production around 2028. Given how much of the global AI chip supply chain already runs through Samsung, that is a serious position to hold. And now the kicker. TSMC controls roughly 90% of the world's advanced AI chip packaging capacity today. 90%. Let that sit. That's not dominance. That's a near monopoly built over decades. But TSMC understands better than anyone that dominance in this industry is never permanent. And in 2024, they revived their glass substrate R&D program. When TSMC treats something as a priority, the entire industry takes notice that same day. And one more player you wouldn't expect, Corning. You know them from Gorilla Glass, the stuff on your phone screen, but their real expertise is specialty glass across fiber optics, pharmaceuticals, aerospace, scientific instruments. That makes Corning a potentially critical upstream supplier, the company that produces the raw semiconductor-grade glass that everyone else then processes. Their investment signals that the supply chain to support all of this is starting to form inside the United States, and that matters enormously because a production ecosystem is only as strong as its weakest link. So put the whole board together and here's what you get. A race that is genuinely, completely undecided. No single company or country has locked up glass substrates. The infrastructure is being built right now, simultaneously, across multiple continents. But the window is not open forever. The hyperscalers and AI chip designers, the people building the data centers and training the models, will start qualifying substrate suppliers over the next 2 to 3 years. And whoever's ready when that qualification starts lands the contracts. The contracts fund the process improvements. The improvements drive better yields and lower costs. And better yields and lower costs lock in the customer for the next decade. This is the exact dynamic that made TSMC untouchable. When TSMC built its lead in the 1990s, it looked incremental. By the time the world understood how dominant it had become, the lead had compounded into something structural. Glass substrates are at an earlier stage of that same compounding curve, right now. And here's the economic reality that makes this window so hard to recover from if you miss it. A single glass substrate production line costs between $500 million and $1 billion to build. And it takes years to qualify with customers because the chip designers have to validate that the substrate works reliably at scale before they bet their products on it. So whoever reaches volume first gets into qualification first. Whoever qualifies first gets the design wins. Whoever gets the design wins accumulates the production experience that pushes yields up and costs down. And there it is again, the loop. Higher yields, lower cost per unit, lower cost, more competitive pricing, more market share, more volume, more experience, higher yields. The loop closes and tightens with every year of production. Companies outside it aren't just behind, they're falling further behind every single quarter. Now, I want to be straight with you because this is where the channels that overhype this stuff get nuked, and I'm not going to do that to you. The lead here is real, but it is not locked in. China moved early and moved seriously, but Intel has the longest track record. Samsung has a live pilot line, TSMC owns 90% of packaging today, and Corning sits on the raw materials. This is a genuine multi-front race, not a finished one. The manufacturing is still hard, the yields aren't solved, and the volume factories serving major AI customers do not fully exist yet, for anybody. Roadmaps targeting 2026, 2027, 2028 are roadmaps, not shipped product, and roadmaps slip. So when you hear China replaced silicon, understand the honest version. China made an aggressive, well-funded early bet on a layer of the supply chain that export controls don't reach. And right now, nobody has won. The next 3 years decide it. Here's the pattern that shows up over and over in technology history. The most consequential shifts almost never look consequential while they're happening. They look small. They look technical. They look like something that belongs in a trade journal, not on a front page. And then years later, everyone who missed it looks back and sees exactly what they were staring at and didn't recognize. The move to glass has that quality. The chip war was fought loudly, publicly, for years. Export controls, subsidies, front-page stories about transistor sizes. All of it real. All of it mattering. But it created tunnel vision, an obsession with one layer of the stack that made it easy to miss what was happening in the layer right below. And what gets built on that layer touches everything. AI training runs on enormous clusters burning power for weeks at a time. Better substrates mean faster data exchange, less wasted energy, training runs that finish sooner, faster model development. Data centers pack more compute into the same floor space and run it more efficiently, so the cost of AI deployment comes down and more of the world can afford it. And it goes wider than AI. Drug discovery, climate modeling, materials research, defense, scientific computing across every field. All of it runs faster when the foundation gets better. The silicon era isn't ending. 50 years of shrinking transistors didn't just stop, but it's being joined by something new. A second axis of improvement, a way to make computing dramatically more powerful that doesn't depend on making transistors smaller. It depends on making the foundation underneath them dramatically better. And the material that unlocks it has been around for thousands of years. Flat, precise, stable under heat, invisible to the conversation until it suddenly wasn't. The AI era may well be built on glass, and the race to own that foundation, to be the company, the country that controls where it gets made, how it gets made, and who gets access to it, is being decided in the years between now and 2028, not in some distant policy debate, not after the next round of export controls, right now, in factories being poured and supply agreements being signed and patent portfolios being built that most people have never heard of. That's what makes this moment so unusual. The outcome is not locked in. The lead that exists today is real, but it is reversible. The companies and countries that recognize what's happening and respond with the seriousness it deserves still have time to shape how this ends. The ones that keep staring at the transistor race while the substrate race runs in parallel may find themselves exactly where a lot of chip companies found themselves when TSMC's lead finally became undeniable, surprised, and very, very late. Here's the question I actually want your answer to. And be honest, because people get heated on this one. Is it a good thing that one country pulls ahead in a technology this foundational? Or does the world run better when no single nation controls the infrastructure everything else depends on? There's a real argument on both sides. Some say competition between countries drives faster innovation and pushes everyone to build better. Others say that when critical technology concentrates in one place, the rest of the world ends up in a position it can't negotiate its way out of. Both have history behind them. Drop your answer in the comments. I read every single one. If this story made you see the chip world differently, hit like. It takes 1 second and it genuinely helps this reach people who'd care. And if you're not subscribed, subscribe and turn on notifications. We cover the moves that happen before the mainstream catches on, and there's a lot more coming. Now, you want to see what happens when you take that same long game thinking and point it at an entire desert? China planted billions of trees across dead, barren land, and scientists had no idea what to expect. 10 years later, the results left researchers speechless. That story's on the screen right now. Click it. You won't regret it.